All right, so we talked briefly last time about this equation, x cubed plus y cubed equal to 6xy. Oh, question. Yeah, thank you. I definitely should. I just can, but I should have it over here. Also, I should grab where's the chat? There we go. Cool. All right, we talked about this equation. By the way, this is a famous equation. It's called the folium of Descartes. Folium of Descartes. And it looks vaguely like this. You can, and you should totally, like, if you have a chance, graph it in Desmos, but you can totally graph things that aren't functions in Desmos just by writing this equation in Desmos. It's kind of nice. But it looks kind of like this. And we found last time, and we'll kind of show the work again, we found at the point 3, 3 that the slope of the tangent line was -1. And the way we found the slope of the tangent line there was by finding the derivative and plugging in point 3, 3. No, actually, I want to do it again just so we can see the work again. Also, because I want to find something else as well. So finding the derivative implicitly, we take the derivative of both sides. We got a 3x squared. The derivative of y cubed is 3 times y squared times the derivative of y. If we're thinking of y as a function of x. And on the right hand side, we have to use the product rule. I'm thinking of it as 6x times y. Although some people like to think of the 6 as being pulled out and think it was just x times y. Either way is fine. I just find it easier to kind of let the 6 live with the x. So that the derivative of 6x is 6 times y, and then 6x times the derivative of y, which is again dy dx. I should mention, if we were just being asked to find the slope of the tangent line at the point 3, 3, now would be the best time to plug in 3 for x and 3 for y and solve for dy dx. On the other hand, if we're being asked to find the derivative in general, which we are in this case, even though I haven't written it, we are, it's better just to go ahead and find dy dx in terms of x and y, and then later on answer the specific questions. And we'll see some examples in a minute where it's going to be better to go ahead and just plug in the point as soon as you have taken the derivative of those sides, even though you haven't found dy dx yet. Here, if we isolate dy dx, we're going to put 3y squared times dy dx minus 6x times dy dx equal to 6y minus 3x squared. Factor out the dy dx, up to 3y squared minus 6x. And then finally divide by this, you get the derivative dy dx equal to 6y minus 3x squared over 3y squared minus 6x. And this can be simplified just a little bit by factoring out 3 from the top and 3 from the bottom. So the dy dx is equal to 2y minus x squared over y squared minus 2x. We did that last time. And then we see that if you plug in the point 3, 3, you do indeed get a derivative that's equal to -1. Great. Another question we would like to answer is, what's the highest point on the loop right there? What is the highest point on the loop? Well, typically to find a highest point on a section of a graph, also known as a local maximum, we have to find a place where the derivative is equal to 0. That's typically where we find local maximum and local minimum, by finding where the derivative is equal to 0, also known as a critical point. So we're going to find the critical points by setting this derivative equal to 0. Now this is going to be a little weird because we're going to get a couple answers here. Let's see. If I set the derivative equal to 0, if I set 2y minus x squared over y squared minus 2x equal to 0, well, I'm only going to worry about setting the top equal to 0, right? Because if I'm trying to have a fraction equal to 0, I want the top equal to 0, and also not the bottom. So I'm actually just going to set 2y minus x squared equal to 0. And solving for y, I get y equal to x squared over 2. Now, that doesn't actually give me a point yet. This needs to be a point on the graph. So what I have to do at this point is I have to plug this y back into the original equation so I can actually find a point that is on this curve, this graph, that also satisfies this particular restriction. Now, I'm going to just say, I bet we're probably going to get 2 points because we're going to get a point here where the slope of the tangent line is 0. We're also going to get a point right here where the slope of this tangent line is also 0, which also is a point where the tangent line is, right? This is kind of, this 0, 0 point is kind of funky because the place where you have both a vertical tangent line and a horizontal tangent line, which is kind of weird. Sometimes that happens with these weird non-function graphs. So if we plug this back into the original equation, I'm going to have x cubed plus x squared over 2 cubed equal to 6x times x squared over 2. That looks kind of dicey. It looks like I don't have enough room to finish this equation, but I probably do. Let's see here. So if we bring everything to the, I don't know, to the right-hand side, I'm going to have 0 on the left equal to, so this is 6x times x squared over 2, which is 3x cubed, and then minus an x cubed, and then minus an x to the 6th over 8. I don't know why I picked the right-hand side. Might not have been the best choice. It's fine. So solving this, we have 0 equal to 2x cubed minus x to the 6th over 8. And I would try to make my life easier by multiplying everything by 8. That seems like something we could do. So I have 0, equal to 16x cubed minus x to the 6th, and then factor out an x cubed. So I do get x equal to 0. And I also get x equal to the cube root of 16, which is not a lovely number, but it is certainly a number that seems like a plausible choice for that point right there, right? We're going to be less than 3, which the cube root of 16 definitely is less than 3. Right? The cube root of 27 is equal to 3, and we're bigger than 2. So that seems like probably where we have. So this seems to be most likely where our loop has a maximum or the highest point on it. I guess since I asked for the point, I should also find the y coordinate. Right? If I was really asking for the point, I'd be like, okay, well, x is the cube root of 16. Now, to find the y coordinate, I don't want to try plugging back into this. I keep going too high here. Sorry. I don't want to try plugging back into this equation and solving for y. I don't have to, because I know that to do this, I should have that y is equal to x squared over 2. So if I'm going to find the y coordinate that goes along with this x coordinate, I'm just going to plug back into this and say, okay, I'm going to get x equal to the cube root of 16. Or maybe we prefer 16 to the 1/3, and y is going to equal 16 to the 1/3 squared over 2, which I probably wouldn't simplify at all. So my coordinate is actually the point 16 to the 1/3, comma 1/2, 16 to the 2/3. Kind of gross, but sometimes the numbers are gross.
I'm a little confused from where we put the derivative equal to 0. So put the derivative equal to 0 to find it.
I wouldn't say that. Well, maybe I would. Yeah, I'd take it back. Yes, I would totally say that. Yeah. So you're right. We set the derivative equal to 0, and then we set specifically the numerator equal to 0 because that's how our fraction is equal to 0. And then we saw that, well, there's a lot of solutions to this equation, right? You get the point 0, 0. You get the point 1 comma. You get the point like 2 comma 2. There's lots of points that satisfy this equaling 0. Not all those points are on this graph, right? The point 2 comma 2 is definitely something that satisfies this equation, where this derivative would equal to 0. But 2 comma 2 is not a point that's on this curve. If you plug in 2 here and 2 here and 2 here and 2 here, you get 8 plus 8 equals 6 times 2 times 2, which isn't true. So what we're doing with this equation is we're isolating y and then we're plugging that back in to the equation for y. So that we can actually then find a point that both satisfies this equation and is a point on the graph. So that's what we're doing with all this work here, is we're plugging that in for y, and then we're solving the system so that we end up getting an x value.
You're saying y equals that, what x value satisfies that y?
Right,
On the graph.
that's on the graph. Yeah. And so we plug it in, we do some algebra, we end up getting that either x is equal to 0 or x is equal to the cube root of 16.
Did you also have to make a situation that the bottom of the function doesn't equal 0?
No, we didn't. But you're not wrong to think about that as well. So you're right. If we end up getting x equal to 0, well, then we would also get y equal to 0. So I will point out that 0, 0 is a point where you've got some weirdness happening. Is a point where we have both a relative minimum and also a vertical tangent. Because this graph is kind of funky in that way, right? At this point here, you have a relative minimum if you're going this way, you have a vertical tangent if you're going that way, and they happen to go through the same shape.
You have to make sure that the bottom of the group is also this.
Right. So what I would say here is that if you got this, so this would be a 0 over 0 type of thing if you're looking at plugging in 0, 0, and to kind of figure out what's going on there, you'd have to use some limits to kind of see if you're talking about a minimum, right? To see if the limit actually existed, depending on which way you're going. And there's a little bit more we have to talk about before we can actually do that. But yes, it's something we should be concerned with. So in general, if you're looking at these curves that are not functions, and you're trying to find where they have a relative extrema, we end up typically setting a fraction equal to 0. And yes, usually we need to have the numerator be 0 and the denominator be not 0. Or if the denominator is 0, do more exploration. Other questions about this again before we do something?
You found the derivative of the original, and whatever it was, like you can solve for y, plug y into the original one.
Right. To find a point.
Yeah.
Right.
And then we put the x.
So I plugged the x back into this equation because I knew that this had to be true to be the point that was at the maximum, right? If we're trying to find this point, we said, oh, we're going to find this point by setting the derivative equal to 0. We set the derivative equal to 0, and we found that y had to equal x squared over 2. So if we're at a relative max or a relative minimum, we know that this relationship has to be true. So if we know what the x value is, then we can plug back into this to find the y value. We could have, although I don't want to, we could have also plugged back into this and tried to find the y value, but it's definitely going to be more work, right? If I plug in x equal to what, the cube root of 16, it's probably not impossible, right? If we plugged in x equal to the cube root of 16, you would get 16 plus y cubed equal to 6 times the cube root of 16 times y. It's not impossible to solve for y there, but it's definitely more work than I want to do. If I can do it this other way. So usually when you're trying to find the y coordinate of something, you always want to look for the easier way to get there because there's usually an easier way. Okay. Yeah.
Can you do a little bit more elaboration on the maximum and the minimum? Because the question is finding the maximum and the minimum.
The question actually wasn't to find the maximum. The question I specifically posed was to find the highest point on the loop, which we definitely did.
Are they going to be asked to find the maximum?
Yes, and to find a relative maximum, relative minimum, we have to talk about the first derivative test, which we haven't quite gotten to yet. So yes, that's definitely something that's coming up in chapter 4. We're for sure going to talk about it. We're just not there yet. Or maybe at least we're not there in this class yet. Maybe some of your classes are there, but we are not there today. Okay, let's do a few more examples because there's a couple things we should talk about when it comes to implicit differentiation. So let's say we had something like, I don't know, x cubed times y to the 4th plus sine of xy equal to e to the x times y cubed. That's a lot of product rule, James. Oh well, such is life. Plus y to the 5th. This is going to be kind of gross. I will just warn you right now. This is going to look ugly. I see a lot of products. I see a product, a product, a product. Yeah, I see 3 product rules we're going to have to use. Oh well. So let's find the derivative. We want to find dy dx, or as I would probably prefer to write, I want to find y prime. And let me just check one thing. Yeah, let's throw in a -1 here just for fun. Not really just for fun, but. Okay, so let's find the derivative. All right, so I'm gonna just differentiate everything again. Taking derivatives of things with x's as you normally would, and things with y's, we're thinking of y as a function of x. So when I differentiate y to the fourth, I'm really thinking of some stuff to the fourth. And the derivative is 4 times my stuff cubed times the derivative of stuff because the change. Or more directly put, whenever you differentiate something with a y in it, you always end up multiplying by y prime. It's another way of thinking about it, although it's a less thoughtful way of thinking about it. So differentiating, we're going to get 3x squared times y to the fourth plus x cubed 4y cubed times y prime. There's your derivative of x cubed y to the fourth. Plus, now I have to do the derivative sine of xy. Derivative sine of some stuff is cosine of the stuff times the derivative of the stuff, which is going to be, another product rule. It's going to be the derivative of x times y plus x times the derivative of y. I'm going to run out of room. All right. So there's my derivative of sine of xy equal to, I'm going to use another line here. The derivative of e to the xy cubed, well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. How many times am I going to say it? So many times. It's going to be e to the xy cubed times the derivative of xy cubed. Product rule again. 1 times y cubed plus x times 3y squared times y prime. Plus the derivative of y to the fifth, which is 5y to the fourth times y prime, minus the derivative of 1, which is 0. I'm going to write these two just to make sure we're super clear. So that's our derivative of e to the xy. And that's our derivative of y to the fifth. And finally, that's a derivative of 1 if you really want. So there's your first step. And usually, although this is kind of terrible, usually the first step isn't too bad. Often with these implicit differentiation problems, when you're trying to find the derivative, it's all the algebra afterwards that's really where it gets ugly. So now we're going to have to do an additional step. That's something you don't have to do, but here we do. So previously, in the last example, after we differentiated both sides, we just brought all of the things that had a derivative to one side and all the things that didn't to the other side. Before we can do that here, we have to distribute. So I have to write out that, well, this is fine. I've got a 3x squared y to the fourth plus, I'm going to rewrite this just slightly, bringing out constants in front. So I've got 4x cubed, y prime. Here I have to distribute. I have to distribute this cosine of xy to each of these terms because one of those terms has a y prime and one of them doesn't. So I'm going to have a cosine of xy times y. And I do encourage you to write the things that aren't in the cosine function in front of it. Otherwise, some people would maybe make the mistake of saying this is cosine of like x times y squared because they would think that the y out here could multiply the y in there. It can't, right? The stuff in there is stuck. One time a student said, it's like cosine's the bodyguard. Cosine's protecting the stuff that's inside it from anything else doing anything to it. So once that stuff's inside the cosine there, this stuff out here can't touch it, being bodyguarded by cosine. Okay, so I've got y times cosine of xy, and then I've got xy prime times cosine of xy. Equal to, same deal here, I have to distribute this, which is kind of awful. So I'm going to have y cubed times e to the xy cubed. And I'm going to have 3xy squared y prime times e to the xy cubed. And finally, the last term plus 5y to the fourth I prime. Barely fit. Okay. So now we have two things we have to do. Thing one, I guess three things really. Step one, bring all the y primes to one side, all the other things to the other side. Step two, factor out the y prime. Step three, divide by what's left over. So I'm going to bring all the things that have a y prime to the same side. It does not matter which side you take. if you pick the opposite side of someone else, the only thing that's gonna be different is your answer will look like the negative of their thing over the negative of their thing. It will just be the same thing. So I'm gonna do 2 steps at once. I'm gonna bring all the y primes to the left, and I'm also gonna factor out the y prime. Not too terrible. So factoring out the y prime, I'm gonna have a 4x cubed y cubed. I'm gonna have an x times cosine of xy. I'm gonna have a minus 3xy squared e to the xy cubed. Man, I made this one a little too awful. And a minus 5y to the 4th, and it's equal to all the other stuff on the other side. So it's going to be a y cubed e to the xy cubed minus a 3x squared y to the 4th minus a y cosine of xy. And then finally, we would take both sides of this equation and divide by the same terrible thing here to get a final answer of y prime equal to all this stuff over here, y cubed e to the xy cubed minus 3x squared y to the 4th minus y cosine of xy over this terrible denominator, 4x cubed y cubed plus x cosine of xy minus 3xy squared e to the xy cubed minus 5y to the 4th. Woo, terrible. So a lot of implicit differentiation problems have is just a bookkeeping problem, right? This problem is really not about your ability to do calculus, although you do have to take the derivative in the first step. But really, after the first step, this problem is, can you keep track of all your pieces? Can you do the algebra correctly and not make a mistake? So I would say you definitely have to be, and this one I would say this is a relatively extreme example. I feel like I made this one a little harder than I meant to, but the idea still persists that we are just differentiating both sides, and then the rest of it is doing some algebra steps, multiplying stuff out if you have to, collecting all your y prime terms on one side, factoring out y prime, and then dividing by what's left over. The process always is the same. Yeah. What are we finding? That's an excellent question. So we are finding the derivative of this function at any point x comma y. So for example, and let me actually look for numbers here. So the problem is, the hard part here is that, yeah, that would probably work. I'm just trying to pick numbers that are not super awful to plug in here. So for example, yeah, so we could say, I want to know what, I'm really hoping the numbers are, yeah, that should be fine. What is the, yeah, it's going to be not very interesting. What is the slope of the tangent line at the point, I don't know, let's say 8, 0. Well, we could plug in 8 for x and 0 for y into this terrible looking derivative and get an answer. And in this case, it's actually not that bad because almost everything is going to be 0 if y is 0. So if we actually plug this in, we would get 0 minus 0 minus 0. Okay, great. It's either going to be 0 or not existing. Hopefully it's 0. And if we plug in the 0 to the bottom and 8 for x, we get 0 plus 8 times cosine of 0 is 8 times 1, which is 8. Minus 0 minus 0. So this example, again, because it's kind of extreme, this example ends up being just 0 when we plug in 0, which is great. So that would mean that the slope of the tangent line at 8, 0, 0, and also the equation of the tangent line is not very exciting, but it would be y equal to 0, right? Because it's a horizontal line, since the slope is 0, and it has to go through that point. So again, this one, if you actually tried to graph this thing that I made up just on the fly here, it's probably not very interesting. It might be very kind of, did you graph it? No, okay, but if you graphed it, it probably is, there's probably like weird stuff going on where you don't get very much defined because of how constrictive it is, because there's too many things going on. That's okay then. We're not being asked to graph it. And you're almost never going to actually be asked to graph something complicated like this. Like I never was when I did plugging. It's not a thing we typically graph, unless it's something relatively easy to graph, like this thing here. This is a fairly well-known graph. It's not too hard to graph, but most of these functions or these equations where you have x's and y's all mixed together, we just kind of pretend like we could have graphed them, find the derivative, and then maybe find the slope or an equation. Now, one thing I want to point out is a lot of the time we are asked to find an equation of a tangent line for these sorts of things. And if I did it this way, I would have said I did too much work. So let me show you what I mean. I don't have any examples. Fine, I'll just make something up, which I can do because I'm not. Yeah. Cool. So let's say we had this not as terrible thing, which I will make up right now, which will turn out just fine. X cubed times y plus y squared equal to, let's make sure it's cool, 8, 1, x squared, let's see, y to the 5th. Sure, that should be fine. 9, let me just check my numbers, 9, 4, 5, oh, that's it. That should be a 4, sorry. Again, it doesn't matter super a lot, but I want to be precise. So there we go. That's a 4. And it doesn't look like a 4, but it is. So what we want to do for this equation, we want to find the equation of the line tangent to the given curve at the point 2, 1. Which I will point out because I actually thought about it. 2, 1 should be a point that is on this graph, and it is. You plug in 2 for x and 1 for y. The left side should equal the right side. Let's double check. You don't actually, what I should say, if someone asks you a question like this on a test, you should never double check there's a point. Because they've either done the work to make sure it is a point, or they didn't and they don't care. And they just want you to take the derivative and find the slope of the tangent line. So it's really on an exam, never in your interest to see if this is actually a point in there, even though it should be. Most people do check, but I've certainly made the mistake in the past of not checking because I didn't think about it. So, but if we plug in 2 for x and 1 for y, we get 8 times 1 plus 1, which is 9. And over here we get 2 squared, which is 4, plus 1, which is 5, plus 4, which is 9. So check that. So now, here's what's going to be different about this process. We're going to take the derivative just like we did before. So differentiate both sides. We're going to get 3x squared times y plus x cubed times the derivative of y plus the derivative of some stuff squared, which is 2 times y times the derivative of y equal to the derivative of x squared plus the derivative of y to the 5th or some stuff to the 5th, which is 5 times my stuff to the 4th times the derivative of my stuff, and then the derivative of 4, which is 0. I do encourage you when you're taking the derivative constant in these problems specifically to actually write it as being 0, just so you remember that it's going to go to 0. Because a lot of times people will accidentally, like a lot of teachers will write this equation as just equal to a constant, and then sometimes I've seen students forget to take the derivative of that constant and just leave it as a constant, same constant. When they take the derivative of both sides, we'll make sure that derivative of that constant is 0. So now, instead of doing all the algebra to solve for y prime, they didn't ask us to find y prime in general as a function of x and y. They just asked us to find the equation of the tangent line at one particular point. So now is the moment to plug in x equal to 2 and y equal to 1. It's going to be easier to find all this stuff. So if we plug in that, let's see what we get. I get 3 times 2 squared times 1 plus 2 cubed times y prime plus 2 times 1 times y prime equal to 2 times 2 plus 5 times 1 to the 4th times y prime. And now solving for y prime is pretty not terrible. Let's see, I've got 8y prime plus 2y prime is 10y prime. Sorry, I should just say 12 plus 10y prime equals 4 plus 5y prime. And then bringing the y primes to the left, I've got 5y prime. Bringing the other stuff to the right, I've got 4 minus 12. So my slope of my tangent line at that particular point is -8/5. To me, that's a lot easier than doing all the algebra of writing y prime equals a bunch of stuff with x's and y's over a bunch of stuff with x's and y's. Which we sometimes do have to do if they've asked us to find the derivative just in general. But if they're just asking us to find the slope of the tangent line or the equation of the tangent line, I really think it's best easiest to just plug in this point as soon as you have, or right after you have taken the derivative. So now we've got a slope. We've got a point. We can find the equation of the tangent line. So I need to move this back. I keep trying to move this forward. So our equation is going to be y minus the y coordinate equal to the slope times x minus the x coordinate. Which you could then solve for y if you felt like you needed to. We would get y equal to -8/5 x plus 16/5 plus another 5/5 is plus 21/5. But I would probably leave it like this so I can get away with it. Sure. So you can definitely start with point slope form, but then you have to simplify it to the slope intercept form, which is fairly standard. Like there is a good reason for writing it like this. There's actually a couple of reasons for writing this. One, it does tell you what the slope, the intercept is, and the slope. But more importantly, writing it like this means you can write it as a function, right? You can say, oh, my function, that's my tangent line, is f of x equal to -8/5 x plus 21/5 y. And while you could kind of do that here, if you're writing as a function of x, it really should be all by itself and everything else should be on the other side. So they're not wrong to say that. It's just, this is also technically correct. Yeah. So I subtracted the 5y prime from both sides. And then I also subtracted 12 from both sides. You can get there however you want. So, and you were gonna but what were you gonna say? Sorry. Oh yeah, sure. Really, so really, I use the same equation. I wrote it this way. I wrote it as y minus y naught equals m times x minus x naught, and I think what you were saying is y equal to y naught plus m times x minus x naught. Yeah, they're the same equation. Now, I will point out, even though this technically is isolating y by itself, you probably are expected to multiply this m by x minus x naught and then actually write it in this simplified version here, where you've got m times x plus this simplified y intercept. Yeah.
So plan notes for I don't think it was implicit differentiation, but it was a similar idea where we were asked to find a tangent line that passes through a specific point, but that point is not on the graph.
Sure.
And that was a little bit tricky.
That's kind of a different thing. We can certainly, you and I can talk about that later. Or maybe later today, but that's kind of, it doesn't really have to do with implicit differentiation. But basically the idea for solving something like that would, you have the slope of the tangent line using the derivative, and you also have the slope of the line you're trying to find that's going through this point that you don't know on the graph, and this other point that you know, so you use the slope equation, and then you set those two slopes equal to each other to solve for the point.
Could that come out with the implicit differentiation?
I mean, I don't feel like it would. No, I mean, I guess technically yes. Usually if we could ask something, yeah, you could. Is it going to be doable? Maybe not. Like, for example, I did go actually later on the other day, I went and graphed log base x of sine of x. It's wild looking. I would encourage you to check it out. It's not a function you're ever going to see, but it looks bizarre. So here's the question that's being asked, or something like it. Let's make it super easy. Let's say we have the function f of x equal to x squared, and we want to know what is the equation of the line tangent to f of x that passes through the point, let's say, I'm going to make something up, hopefully it'll work out okay. Let's say the point, let me search for a real here. 1, 2, 2. Sure. 0.2, 3, 3, 5. Sure, let's try that. This one might be a little too easy, but it'll be fine. So here's the situation. We've got this graph. We've got this point over here, 3, 5. What we're saying is there's some point, or maybe more than one point, right? So, right, there could be multiple points where there's a tangent line that goes straight through that point. So there probably is actually two answers here. Because there's probably an answer here, and there's probably some answer way up here, where the tangent line goes to that point as well, like that. So there's potentially two answers where there's some point up there where it's tangent. So the idea when you're asked to do this sort of thing is to find the slope of this line in two different ways. So I know this point is 3, 5. And I know this point is, I don't know what this point is. It's x, x squared. You could say x, y, but it's better to say x. Actually, I probably shouldn't use x. No, it's fine. Yeah. So one way to write the slope would be the slope equation. Difference in the y's over difference in the x's. So it's going to equal 5 minus x squared over 3 minus x. Or maybe it's better to subtract the other way. I don't know. Probably doesn't matter. The other way to find the slope is to use the derivative. So the slope of this function, right, f prime of x is equal to 2x. And then we're going to set these two things equal to each other and hopefully be able to solve for x. So I'm going to set, right, because if we know the point, the slope of this line through these 2 points should be the same as the slope of this tangent line. They're the same line. So we're setting those two slopes equal to each other. Multiply both sides by the denominator. We're going to get 2x times 3 minus x equal to 5 minus x squared. Distribute, we get 6x minus 2x squared equal to 5 minus x squared. Bring everything to the right. So I'm adding 2x squared. So 2x squared minus x squared is x squared minus 6x plus 5. Factoring, and it does factor, is x minus 5 times x minus 1. So it looks like the points we're looking at are either x equal to 1 or x equal to 5. If x is equal to 1, what's the slope of our tangent line? Yeah, 2, right? We can you can do it the hard way and say it's 5 minus 1 squared over 3 minus 1, or you can do it the easy way and say it's 2 times 1. So here our slope is going to be 1, and our equation is going to be, 2, thank you. Our slope is going to be 2, and our equation is going to be y minus the y coordinate, which is 1, because if you're plugging in 1, the y coordinate is 1, equal to the slope times x minus 1. And then you can find y, but I don't want to do that. Or if your x value is 5, your slope is 10, and your y coordinate is 5 squared, which is 25. So your equation is y minus 25 equals your slope times x minus 5. So both of those are equations that would, right? So this line is clearly the one that's y minus 1 equal to 2 times x minus 1. And this other crazy line that's tangent way up here at 5, 25 is the y minus 25 equal to 10 times x minus 5. That's all the points. So I would say this point here, 1, 1, and this point here, 5, 25, are the points where the line tangent to the graph happens to also go through the point 3, 5. Is that what we're saying?
Find the slope of both. You think the derivative of the function itself, and then the slope for like the 3, 5. Set them equal to each other. Find the x coordinates. Plug them into like the derivative of the function, and then back into like the slope from find the equation.
Yeah.
So I'm a little bit confused with why you're equating them. If we know the slope of the tangent line, couldn't we just plug that in with 3 and 5?
3 and 5 isn't a point on the graph.
So if we did that, the line we get would be the line of the graph.
Because I want to point out, right, when you're using the derivative tells you the slope of the line tangent to the graph at the point on the graph. That point, not on the graph. I can't plug in that point to find the slope of my tangent line. It's not going to tell me anything.
That's why we need another point.
Right. The m isn't any point. The x, x squared is. Sure, that slope is 5 minus any y coordinate over x3 minus any x coordinate on the graph.
There's a point where the slope of the tangent line equals the slope of some line that passes through 5 and 3, and also passes through x squared.
Right. Although I still use the x and x squared. And 3 and 5. Yeah. I mean. I guess the real answer is experience. I've seen problems like this before. But the idea here is that I'm kind of just using all the information I've got. So if I'm trying to find an equation of a line, and I know it goes through this point, and it has to be tangent to this point, there's only so much I can say. And all I can really say is, well, I can calculate the slope in a couple different ways. One way of calculating the slope, take the derivative of find the slope of the tangent line. Another way of calculating the slope, well, I've kind of got 2 points. I'm trying to find this point. I've got this point, so I can use the slope equation. So the idea with this is really to set both slopes equal to each other. That's how we typically solve this sort of situation. And just because I don't really know any other thing I could do after that, right? I don't have any other information that's going to help me figure out what's going on. So I guess I could pretend like that's how I knew what I was supposed to do, but really it's because I've seen problems like this many times. I'm like, oh yeah, this is what we do. So part of learning how to do math is the experience of doing the math. Be like, okay, I've seen it this way. Now I can kind of try to do it myself. So I would encourage you all. In fact, I'll try and find a problem later on to post on Canvas to try another problem like this when you have a moment, because it's not a bad problem. Like it's a relatively reasonable test kind of problem. I could totally see I feel like this is kind of on the harder side on a test question, but certainly not out of bounds. So it's something I've certainly asked on tests before. I think it's a reasonable question, and it makes people really think about, okay, what's really going on here? Right? It's not just kind of a plug and chug thing. You can't just, if you don't really know what you're doing, it's hard to figure out what's going on here. But if you have an idea of what's going on, like, okay, yeah, I can suss this out. Okay. So let me see here. We should do a little bit more implicit. Yeah. Why don't you all try find y prime, or if you prefer dy dx for the following situation. You've got x to the 4th times y cubed equal to e to the y plus y squared. So many y primes, they're plus x cubed there. Try finding y prime for that. And I'll remind you, whenever you differentiate something with a y, you're going to end up getting a y prime in that term. You should try it at home as well. Also, here's the attendance form in case you didn't get it. Give you a couple minutes to work on that. Let's see. Okay. Okay.
just writing this stuff. I don't
Yeah.
think
Yeah, I mean, I also do that sometimes. I say one thing, I write another thing. Sometimes your brain is really, the truth is. Why that usually happens for me, at least, is because I'm saying one thing, but I'm thinking about the next thing I'm gonna write, and then I accidentally write the thing I'm gonna write next, and that's wrong. So let's see what we've got here. For x to the fourth times y cubed, we're gonna have to use the product rule. The derivative is gonna be 4x cubed times y cubed left alone, plus leave x to the fourth alone, and the derivative of some stuff cubed is 3 times your stuff squared times the derivative of your stuff. The derivative of e to the y, well, that's e to the stuff. And so the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Plus some stuff squared, the derivative is 2 times my stuff to the first times the derivative of my stuff. And then finally, the derivative of x cubed is 3x squared. And then we do the algebra. So, okay, there's a y prime, there's a y prime, there's a y prime. So we bring all the y primes to one side, all the not y primes to the other side. Doesn't really matter. I'm going to do it the opposite way I usually do, just to change it up for so let's bring all the not y primes to the left. So we've got 4x cubed, y cubed, minus that 3x squared. It's equal to all the y prime terms on the right. So e to the y times y prime plus 2y times y prime minus this term here, which is 3x to the fourth y squared times y prime. Then we factor out a y prime. So we get y prime times e to the y plus 2y minus 3x to the fourth y squared equal to same stuff on the left. And then finally we divide by what we're multiplying y prime by, so we get y prime equal to 4x cubed y cubed minus 3x squared divided by e to the y plus 2y minus 3x to the fourth y squared. As a follow-up, I want to point out, we could totally ask, what is the slope of the line tangent to the graph at the point, well, that was a good point here, 0, -1. So one way to do this, since we've already done the work, would just be to plug this into our derivative. If we plug that in, let's see what happens. So y prime, you can either write y prime evaluated at 0, -1 like this, or you can write it as y prime evaluated at 0, -1 like that. There's both ways to say plug in 0, -1. We don't typically use this notation though. Like if you wrote dy dx, you don't usually write dy dx parentheses 0, -1. It's kind of really unwieldy. So if you're writing dy dx as your derivative, then you usually use this vertical line with a little subscript of your point to say that you're plugging in that point to that derivative. Either way, if we plug it in, we're going to get, let's see, I'm going to get 4 times -1 cubed times 0. So I'm going to get 0 minus 3 times -1 squared over e to the 0, which is 1, plus 2 times 0 minus 3 times 0. So I end up with -3 over 1. Or -3. There's the slope of my tangent line. Now, what I want you to see again, because I do think it's worth seeing, is if they had only asked us to find the slope of the tangent line at point 0, -1, instead of asking us to find the derivative, we could have just taken the derivative both sides, and then at this juncture right here, after we've taken the derivative, we then could have plugged in the point, so you can see that. We could have plugged in 0, -1. And look how easy it becomes if we plug in 0 for y and -1 for x. 0, 0, e to the 0 times y prime, 0, 3. That is really easy to find y prime if they're just asking us to find at this particular point. And this one's extra easy because one of the things is 0. But doing this, we get y prime equal to -3. So I really want to make a strong case for if they're just asking you to find the slope of the tangent line at a particular point, take the derivative of both sides and then immediately plug in that point. So I wouldn't say I'm multiplying by y prime, I mean, I am, but what I'm really doing is I'm using the chain rule here. So what's happening is when I differentiate y cubed, in fact, let me show you, let's look at another example to kind of explain what I mean. So let's say we had something like, not too terrible here. Let's say we had y to the fifth plus x cubed equal to sine of y plus x times y squared. So here's the idea. Y is we're pretending y is a function of x. What we're really saying to ourselves inside our heads is, well, it's not really a function of x, but it depends on x a whole lot. So we could write this if we wanted to. We're saying y essentially is a function of x. So if I wanted to, although I don't really want to, because it's very it just takes up a lot of space, I could totally rewrite this as f of x to the fifth power plus x cubed equal to sine of f of x plus x times f of x squared. And so now if I'm going to differentiate both sides, we have a power rule version of the chain rule that says, oh, if you've got some function to a power, the derivative of f of x to the power is 5 times f of x to the fourth, but then what do I have to multiply by? F prime of x, right? The chain rule, we have to multiply by the derivative of the inside or the derivative of the stuff. That's what we're doing when we write it up here. We're just not quite writing, right? I'm going to say the derivative here is 5y to the fourth times y prime. It's the same deal. I'm just using y instead of f of x and y prime instead of f prime of x. And so if we kept going, the derivative of x cubed is just 3x squared. The derivative of sine of some stuff is cosine of that function or that stuff times the derivative of that stuff, because we always have to multiply by the derivative of the inside if we're using the chain rule. And then lastly, if I have x times some stuff squared, I'm going to use the product rule and get 1 times the other thing left alone plus x times the derivative of this is going to be, well, I've got some stuff squared, so it's going to be 2 times my stuff. That's going to fit. Come on, fit. Times the derivative of my stuff. It barely fits. Sorry, that's terrible. That's awful. Okay, that's x times 2 f of x to the first times f prime of x. So that's what's happening. But again, we're trying to kind of, for lack of a better word, save space. Instead of writing f of x and all this, we're just going to write y. So the derivative of y to the fifth is 5y to the fourth y prime. The derivative of x cubed is 3x squared. The derivative of sine of some stuff is cosine of the stuff. Chain rule times the stuff. Product rule here, derivative of x is 1, leave y squared alone, leave x alone, and the derivative of some stuff squared, just like over here, is 2 times my function to the first power times the derivative of my function. This actually is a good reason to not use y prime and to use dy dx instead, because if you're not super duper careful, your y to the first and your y prime can look a lot the same. I wouldn't write y to the first usually, but I wanted to really emphasize what's happening here.
So as far as isolating y prime goes, it's always going to be super easy because we can't have y prime squared.
Right, you shouldn't, it should always be relatively easy. The only thing that sometimes is challenging is sometimes you'll have like a cosine of something and then times a product rule thing, and then you have to do some distributing. But right, you shouldn't ever be able to get y prime to a power. You should only ever have y prime to, because it's only ever coming up after you've done the derivative of stuff and then multiply by the derivative of the inside stuff, which is y prime. Okay, you shouldn't be able to get y prime squared or any other weird funky power of y prime. Cool. So implicit differentiation is a pretty powerful tool. It definitely allows us to handle functions where the x's and y's are kind of all mixed together. But it also allows us to do some other stuff, like find the derivative of the natural log of x. So I know we talked about the derivative of the natural log of x last time, and we did kind of the limit definition, but there's actually a much easier way of getting there. So if I want to find the f prime of x or f of x equal to the natural log of x, here's another way to get there. start with y equal to the natural log of x, and then rewrite it as an exponential equation. So instead of y equal to the natural log of x, we can have e to the y equal to x. All right, that's the same thing. And now we can use implicit differentiation to differentiate both sides. So we're going to differentiate. And what's the derivative of e? In fact, let me write down. We're going to differentiate. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff.
I thought, like, that the derivative of e was just.
So here's what I would say. The derivative of e to the x is e to the x. Let me ask you all a different question real quick. What's the derivative of e to the x squared? It's e to the x squared times the derivative of the stuff.
So it's only when it's e to the x.
Right. So here's what I would say. We have all these rules for derivatives. We know how to find the derivative of sine, cosine, tangent, secant, cosine, cotangent. We know how to find the derivative of x to a power. We know how to find the derivative of e to the x and natural log of x. And as long as the argument of that function is just a single x, the rule is just the very basic kind of whatever. But every function that we know how to differentiate also has a chain rule version of that function, which is to say, okay, if instead of your function evaluated at x, if it's instead your function at some stuff, you do the same sort of rule, but then you have to end up multiplying by the derivative of the stuff. So here, since our y is a function of x, the derivative is e to the y times the derivative of that function of x. And then what's the derivative of x? 1. But look, now I can solve for dy dx, which is what I'm trying to find, because y is equal to the natural log of x, and I want to find the derivative of y, the derivative of the natural log of x. So check this out. We're going to solve for dy dx. So dy dx is equal to 1 over e to the y, which doesn't seem super helpful until we remember that e to the y is indeed equal to x. So this is really equal to 1 over x. So, oh, great. We have shown that the derivative of the natural log of x is, in fact, 1 over x. It's a much slicker way of doing it. But the problem, or the thing about doing it this way, is you have to have the other derivative. So to be able to find the derivative of natural log of x implicitly, you have to know the derivative of e to the x. And vice versa. If you want, you could, there's also a similar proof for finding the derivative of e to the x implicitly, but you have to know the derivative of natural log of x. So, yeah. And actually, that's kind of the general thing. You can always, if you have a function that has an inverse function, you can find the derivative of it by using the derivative of the inverse. And there's a whole kind of theorem about that, which we're not going to get too into right now. Yeah. So your question actually made me want, I want to kind of back up for just a second, kind of show you and write down some stuff for you all. You don't need to write this down necessarily, but I think it's worth pointing out the following. So here's often how books write things. We have the derivative of sine of x is equal to cosine of x. And then we also have the chain rule version, which is usually written in the following way. The derivative of sine of u is equal to cosine of u times, some people just write du, I prefer to write du dx. Or in other words, the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. And we're making the assumption, or we're pointing out, u is a function of x. So u is u of x. Yes. The first one is the base case of the second one, right? You could say derivative sine of x is cosine of x times the derivative of x with respect to x, which is 1. So most of the time, well, no, I wouldn't say that. Most of the time, books do talk about both versions because they want to show you the nice version first, because that's the version you typically see. But then we say, well, we can extend this. This is true for any function we talked about. So the derivative of cosine of x is negative sine of x, and the derivative of cosine of some stuff is negative sign of the stuff times the derivative of the stuff. All right, let's just write them all down. We might as well make a whole list. Derivative of tangent of x is secant squared of x. Derivative of tangent of some stuff is secant squared of the stuff times the derivative of the stuff. The pattern is not going to change. It's always going to be take your original rule and replace your x with some stuff and then multiply by the derivative of that stuff at the end. That is the chain rule. So what else? We've got other trig functions. The derivative of cosecant of x is negative cosecant of x times cotangent of x. It's kind of extra funky for cosecant and cotangent, or for cosecant and secant, because you have your stuff show up twice, which is kind of weird. Right? The x shows up twice in your answer, which is kind of abnormal. In most functions, your input only shows up once in your derivative. There are some exceptions. So the derivative here of cosecant of u would be negative cosecant of u times cotangent of u times the derivative of the stuff. You do not. Because again, the thing you should be thinking of, right, is, so if you're taking the derivative of a function of some stuff, you take the derivative of the outer function, you leave the inputs alone. Great. Derivative cosine of x is negative cosecant x cotangent x. The derivative cosecant of some stuff is negative cosecant of you leave that stuff alone, and cotangent of you leave that stuff alone. And then we multiply by the derivative of the inside stuff, but only once. Because that's what the chain rule says. You only multiply by the derivative of the inside stuff one time. Even if it shows up more than one time. And then the derivative of, what would be next? Secant of x is secant of x times tangent of x. And the chain rule version is not going to surprise anyone. The derivative of secant of some stuff is secant of the stuff times tangent of the stuff times the derivative of the stuff. Last trig one, derivative of cotangent of x is negative cosecant squared of x. The derivative of cotangent of u is negative cosecant squared of u times the derivative of u. Okay, what else have we got? We've got the derivative of e to the x is e to the x. The derivative of e to the u is e to the u times the derivative of u. The derivative of the natural log of x is 1 over x. And the derivative of the natural log of u is 1 over u times u dx. We missing anything? Well, I'm not going to write them. But but we will actually talk about those shortly here. The only other thing we're missing is x to the n. So if you have the derivative of x to a power, it's n times x to the 1 less power. And similarly, the derivative of a function of x to a power is n times that function of x, the 1 less power times the derivative of u. So here's all of our standard kind of derivative rules, and here are other chain rule versions. Or don't memorize this, and just remember that if the input is more complicated than just x, you always have to be using the chain rule and multiplying by the derivative of that inside stuff at the end of the day.
One thing that I'm not sure if today would be the right time to ask, so in general, we can cover it at some point. I don't understand why we are applying the chain rule all the time. Like conceptually, why is it?
Because it's applicable. I mean, because the chain rule is for a function of a function.
Right, but I'm not sure if I understand why we have to do the derivative of the inside also. Why can't it just not be the derivative of the outside? Like why are we on this?
Well, because I mean, the short answer is because it's not right. I mean, but like, for example, like if I want to take the derivative of sine of x squared plus 3, it's not just cosine of x squared plus 3. That's wrong.
Yeah.
Because the chain rule says if you're taking the derivative of some function of a function, it's got to be f prime of g of x times g prime of x. We could prove it doing the limit definition. I'm not going to because it's time consuming, but there's definitely a proof in your book, or there should be, where they prove the chain rule the same sort of way, although it's a little more complicated as we prove the product and the quotient rule. So, yeah, we always end up having to multiply by the derivative inside there.
There's no intuitive way of thinking about it, except on the negative.
I mean, I wouldn't say that exactly. I would encourage you to, we're not gonna do this right now because I want to go into things, but I would encourage you to take the derivative of this x cubed plus 1 to the 4th power by 1 chain rule, and by 2 multiply it out first. And you'll see that they have to be the same. And so if you don't have the chain rule part, then it's not going to be what the derivative actually should be. Okay. So logarithms have some interesting things that happen when you try to take derivatives of them. I said it was going to time. All right. There's always so many things to say. So I guess okay, we're not going to go that way just yet. Fine. So I wanted to briefly talk about derivatives of inverse street functions, because I know that they were asked about last time, and this is kind of the right juncture to mention. So in the same sort, we'll just do a couple of them, and then we'll come back around to the physics things. So what if I wanted to find the derivative of the inverse sine of x? Or as I often prefer to write it, the derivative of the arc sine of x. Well, we're going to use the same idea that we just used to find the derivative of the natural log of x, which is that we're going to rewrite it. So first of all, I suppose I should say, what is the inverse sine function? It's kind of funky. Well, if I want to find the inverse sine function, I'm literally taking y equal to sine of x, which is your usual lovely sine function. And we're going to invert it. And the way you invert a function is by switching x and y. The problem here is that if you switch x and y, you don't get a function. That's not a function. It looks like this. It looks like this on the y-axis. So let's see, I'm kind of bad at drawing this, but fine. It looks kind of like this. There's your x equals sine of y. And I hope we can all agree that's not a function, right? It fails the vertical line test hard, right? Almost any vertical line you draw that passes through a point passes through many infinite number of points. So this is definitely not a function. So what we have to do to make it a function is we have to restrict the domain of the original thing we inverted. So we're going to take this original thing we inverted, and we're just going to go from here, the point negative pi over 2 comma negative 1 to here, point pi over 2 comma 1. Because this little section of it is 1 to 1, meaning this little section of it is a function. That's the point negative 1 comma negative pi over 2, just switching x and y. That's the point 1 comma pi over 2. So this inverse sine function is what we actually want to take the derivative of. So here's good old inverse sine. It's not a very, it's not a very big function in that its domain is very limited. It starts at the point negative 1 negative pi over 2 and ends at the point positive 1 positive pi over 2. Like that. So the way we differentiate it, though, is we abuse this relationship that if y equals inverse sine of x, what does it even mean? Sorry, and I'm taking, yeah. So what does it mean to be the inverse sine of x? Well, if I want to say that y equals inverse sine of x, that's the same as saying x equals sine of y. So y equals the inverse sine of x is essentially equivalent to saying x equals the sine of y. And that's actually how I really would encourage you to think about it. If someone said, hey, what's the inverse sine of 1/2? I'm thinking about the inverse sine of 1/2 being equal to some y, which is equivalent to 1/2 equaling the sine of that y. Or as I like to read this, which I strongly encourage, the inverse sine of 1/2 is the angle that if we took sine of it, we would get 1/2. Which I know is a lot to write out, which is why I usually just think of it. What angle is that? What angle can you take sine of and get 1/2? Yes, I was like 5 or 6, yeah, 5 or 6. So here, the inverse sine of 1/2 is equal to 5 or 6. So that's kind of the idea, very, very briefly about what the inverse trig functions do. They take kind of your output value and spit back at you the angle you would have had to take the trig function up to get that output value. But now, how do we find the derivative? Well, we're going to start with y equal to the inverse sine of x. And our desire here is to find the derivative, meaning we want to find dy dx. That's what our goal. So just like with any function that's an inverse of some other function that we don't know how to deal with, we could, although we're not going to, we could use limit definition. I have no idea how to do that. Like, maybe it's doable. I've never seen anyone do it. It's probably doable in some way, but it's probably super weird. But yeah, but that's all we're going to do. Instead, if you have a function that's a known inverse, or specifically, right, the inverse sign is literally defined as take this sine function and invert it. Kind of like the logarithm is really just the inverse of the exponential function, right? That's kind of how we got to it. So I'm going to rewrite this. I'm going to say instead of y equal to the inverse sine of x, I'm going to take sine of both sides, or just rewrite it as sine of y equal to x. All right. What's the derivative of sine of some stuff? Oh, it's cosine of that stuff. But what do I have to multiply by? Yeah, derivative of the stuff. What's the derivative of x? So now we're going to solve for dy dx, but as is typical, we're a little sad because dy dx is going to be 1 over something with y's in it. We need to deal with. Because if your original function is a function of x, your derivative should also be a function of x. So how are we going to deal with that? Well, this is where you can do one of two things. And I would certainly recommend I would recommend using a triangle. I know it might sound kind of oblique, but here's what I mean. So we know from this relationship right here, sine of y is equal to x. So y is the angle, and it's equal to x, which is the ratio of the opposite over the hypotenuse to the sine. So here's what I would actually say. I would say I'm going to write sine of y equals, instead of saying it's just x, I'm going to write it as x over 1. That is the opposite over the hypotenuse. So I'm going to draw a triangle where the angle here is y, and the opposite side is x, and the hypotenuse side is 1. And then we can use the Pythagorean theorem to find the other side, which will be the square root of 1 minus x squared. Okay, so now if I want to find cosine of y, I look at this triangle and say it's the adjacent over the hypotenuse, which is just the square root of 1 minus x squared over 1, which is the square root of 1 minus x squared. So it ends up being 1 over the square root of 1 minus x squared, which is the derivative of the inverse sine function. So the derivative of the inverse sine of x is in fact 1 over the square root of 1 minus x squared. Kind of cool. One more thing about, well, two more things about this. You don't have to do it the triangle way, but I recommend doing so for all these inverse trig functions, which we'll talk more about next time probably. You can resolve this last part by doing this triangle thing. And I recommend doing this triangle thing because it's a thing you're going to want to do next quarter in 21B when you start talking about trig substitution for intervals, which is a method of integration. And definitely using this triangle idea, it's not exactly the same, but it's very similar to this. I would encourage you to get accustomed to this. But if you don't like this, the other way you could go is trig identity. We definitely know trig identity involving sine and cosine. It's sine squared of y plus cosine squared of y equals 1. So if I want to figure out what cosine of y is, I can say, oh, cosine squared of y is 1 minus sine squared of y. And cosine of y is the square root of 1 minus sine squared of y. Yes, I'm ignoring the plus or minus. There's a valid reason for doing so, which I will mention in a moment here. But sine of y is just x. So this is really equal to the square root of 1 minus x squared, which is exactly what we got in the denominator. So you can either use a triangle or the trig identity. They're really the same thing because these are the Pythagorean trig identities, and they come from using the Pythagorean theorem in this triangle. The reason we're able to ignore the plus or minus here that would have been here is because the inverse sine function, or the inverse sine function has outputs between negative pi over 2 and pi over 2, which is the first and the fourth quadrant, where cosine happens to be positive. So cosine of y has to be positive because our angle is living in the first and the fourth quadrant.
You mean first and second?
Nope, I mean first and fourth.
Or cosine is positive? You're right.
It's a different argument when, so later on next week, when we talk about some of the other ones, you can make a similar argument be for the derivative cosine of y always being its correct sign, because the inverse sine function, or sorry, vice versa. The inverse cosine function essentially is between quadrants 1 and 2, and so the sine of the angle will be positive because you're in quadrants 1 and 2. So they all basically, the nice thing about these inverse trig functions is the sign SIGN, the signs always work out the way they need to work out without any. Well, mostly, there's okay, it's a lie. There's some issues, but we'll deal with it. Okay, so I would encourage all of you, when you have a moment, to do the same sort of thing for tangent. So I would, if everyone, not right now, because we're going to finally do the other thing I said, but if you wanted to find the derivative of, say, y equal to the inverse tangent of x, you can do the same thing. You could write tangent of y equal to x and then differentiate both sides and get secant squared of y times y prime equal to 1. And then you can solve for y prime. And then you could figure out what secant of y is by using a triangle. And eventually, if you do this, you should get this is equal to 1 over x squared plus 1. Kind of neat. Okay, so I know I feel like I'm kind of rushing. So the other thing we wanted to talk about a little bit was some examples of some motion stuff. So let's say we've got the following situation. Let's see, actually, let me double check here. Sure, yeah. So a rock, who's throwing rocks? A rock is thrown straight upwards. Off the top of a 64-foot tall building. With an initial velocity, and starting to go, of 48 feet per second. The height or position of the rock, actually, no, we're not there yet, sorry. Of the rock at time t is given by the following equation. Height at time t is equal to, all right, so here's what you should know about this equation. The general form for this equation is in US units, negative 16t squared plus v naught t plus h naught. V naught's your initial velocity or speed. H naught is your initial height. in this particular case, it's going to equal negative 16t squared plus 48 times t plus 64 feet. Right, it's measured in feet. Okay, so what kind of things can we ask? Well, someone might want to know, how fast is the rock going? Or traveling, I suppose is a better word there. After 1/2 a second. Or in other words, what is the instantaneous velocity in 1/2 a second? So the way we find velocity, we know position is by finding the derivative. So velocity is the derivative of position, and it's equal to, in this case, negative 32t plus 48. Or more generally, negative 32t plus v naught. And again, I should say this is specifically for objects that are falling, right? Or going up and then falling, right? If it's only being impacted by gravity, then this is kind of the situation we deal with. There are certainly other position equations someone could make up for like a car or something else, and you don't have this specific one. But this is the very specific general equation for object that is being thrown into the air or is falling in the air or whatever. So to answer this particular question, we're just going to plug in 1/2 and get negative 32t. Sorry, negative 32 times 1/2 plus 48, which is negative 16 plus 48, which is 32 feet per second. So after the rock has been traveling for 1/2 a second after I threw it, it slowed down a little bit, right? It's only going 32 feet per second instead of the initial velocity of 48 feet per second. Which makes sense if you think about the effect of gravity, because gravity essentially is slowing this rock down at 32 feet per second. So every second that goes by, the rock is going to be going 32 feet per second slower. So I would expect that after a full second, the rock will have lost 32 feet per second and will now only be traveling at 16 feet per second, which is correct. If I said what's v of 1, the speed of the rock or the velocity of the rock, I really should say velocity of the rock after 1 second, it's going to be negative 32 times 1 plus 48, which is going to be 16. I mean, you can even see it in this equation. The equation is literally, for every second that goes by, the rock's going to lose 32 feet per second of speed. It's right there. Yeah. I would say no, but I would say it's something to be aware of so that you can kind of check that the work you're doing is right. But typically, if someone's asking me how fast is the thing going, as long as all the units, as long as someone's not like using feet over here and miles over here, like as long as they're not being, right? Like as long as you've got the nice, like everything's in the same sort of units, then I just know my answer is going to be the appropriate unit. So if I know that my position is being measured in feet and my time is being measured in second, I'm being asked about velocity, it's going to be feet per second. Whereas if I'm being asked about acceleration, it's going to be feet per second or feet per second squared. Someone asked me about jerk, which no one's ever going to ask you about jerk. It'd be feet per second cubed. Right? Jerk is like when your acceleration changes. So if you've ever been driving and accelerating and then like slammed on the gas to accelerate faster, that's a jerk because you literally jerk forward. Or if you, I guess, slam on the brakes, you jerk backwards. So jerk is the third derivative. I don't know what a good interpretation for the fourth derivative is, but it's always fun to talk about jerk. So what else can we ask here? Oh yeah, there's lots of good questions here. So how fast is the rock accelerating after 2 seconds? Well, our position was negative 16t squared plus 48t. Sorry, yeah, that's right, plus 64. Our velocity was the derivative of that, which is negative 32t plus 48. And acceleration is the derivative of velocity, or the rate of change of the rate of change, right? When you're talking about accelerating, you're talking about how the speed is changing, how the velocity is changing. And that's just gonna be negative 32 feet per second squared. And it doesn't matter what time it's at for this particular example, because when you talk about an object falling or being thrown or whatever, acceleration is constant. Acceleration due to gravity in the US system is negative 32 feet per second squared. In the metric system, it's negative 9.8 meters per second squared. So those are things that come. And then typically in Calc 2, you take this equation and you reverse engineer it so you can get back to the this equation by doing some anti-differentiating later on.
Actually, our professor did that.
Okay, sometimes they do it, sometimes they don't.
Because especially the C part, if it's adding the constant, it's something that comes up a lot. So do we need to be aware of antiderivative for that?
I mean, I can't say one way or the other. Some people might say yes, some people might say no. It really depends on your professor. I would say it's not unreasonable to say that if the derivative of this is equal to that, then the antiderivative of this is equal to that. So if I know that the derivative of velocity is acceleration, I know the antiderivative of acceleration is velocity. So if I was being told that the acceleration due to time was negative 32, and I wanted to find the function whose derivative was equal to that, I would say, well, okay, the velocity, I know if I want my derivative to be negative 32, my function needs to be negative 32t, and then I can slap on any constant I want, because what's the derivative of constant? 0. But then I have to actually say, well, it can't just be any constant, because I was told very specifically that the initial velocity was equal to 48 feet per second. So I have to use that information to say, oh, well, if I plug in t equal to 0, I should get v of 0 equal to 48. But if I plug in t equals 0 here, v of 0 is negative 32 times 0 plus c, which has to equal 48. So we end up getting that c had to be 48. Yeah. No, it means the acceleration is always negative 32 no matter what. Yeah. Yes. So here's the deal. We throw this rock into the air. After 1 second, it's slowed down by 30 seconds. After another second, it's slowed down by another 30 seconds. So every second that continues on until the rock eventually hits the ground, it's decreasing by 30 feet per second every second. Totally different situation then. Yeah, so if you had some other object, maybe but yes, so you could totally have a different situation. Like, for example, if your position was given by something, like maybe you've got some particle that's moving through space that's got its own kind of energy source, and it's not just completely at the whim of gravity, it can propel itself. Like you could have something like maybe your height is given by t at, let's say, negative t cubed plus 10t squared minus 5t plus 1, right? Then this thing would have an acceleration that would vary at different points in time, because your acceleration would still depend on what time was. Right, here's your velocity at time t, and here's your acceleration, just the derivative at time t. So here in the beginning, your acceleration is a little bit positive, but eventually it's going to be negative depending on what time it is. So yeah. So, but I would say when you're specifically talking about objects falling in space, in the Earth's atmosphere, our acceleration is a constant. The other types of questions that people often like to ask are the following for this kind of situation. What's the maximum height of the rock? This is a favorite. So here's what I want to think about. The rock's going up. In fact, let me draw. So, right, we've thrown this rock from the roof of this 64-foot high building. It's going up, 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 and then eventually it tops out and then starts going down, 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 down. And here's what I would encourage you all to think about. As the rock is going up, in fact, we should be, so back a little. So we should think of the up direction as the positive direction, and the down direction is the negative direction, typically. So as we go up, we would say our velocity is positive because the position is increasing. Whereas if the rock's going downward, the velocity is negative. So when you switch from going up with a positive velocity to going down with a negative velocity, we pass through the point where the velocity had to have been zero. So the maximum height of the rock is going to be found. That's when the velocity is equal to zero. Which makes a lot of sense in the same context as before, that when you're trying to find, say, I don't know, a point on a graph where you might have a horizontal tangent line, you're trying to find where the derivative of your function is zero, which is exactly what we're doing, because we're taking our function h of t equal to negative 16t squared plus 48t plus 64, and taking its derivative, aka the velocity, and setting it equal to zero. And solving this, you get, I mean, you can factor out a 16 here to make life easier, or negative 16. You're left with a 2t minus 3. So you're getting t equal to positive 3/2, or 1.5 if you like. So after 1.5 seconds, the rock hits a maximum height. Now that doesn't answer the question, right? The question wasn't what time is it when the rock reaches the maximum height. The question was, what is the maximum height of the rock? So now that we know when the maximum height occurs, we have to take that number and plug it back into the height equation to find what the maximum height actually is. So the maximum height is going to be the height function evaluated at 1.5 seconds. And I prefer to use a fraction. So plugging that in, we're going to get negative 16 times 3 over 2 squared plus 48 times 3 over 2 plus 64, which ends up being negative 16 times 9 over 4 plus 48 times 3 over 2, which is 24 times 3 plus 64. Excuse me. So we get negative 4 times 9, so negative 36 plus 72 plus 64, which is, sorry, negative 36. I think that's the two I was going to write later. Plus 72 is positive 36 plus 64 is exactly 100 feet high. That's the maximum height of this particular rock that was thrown.
So we don't use sign charts for that.
I wouldn't say so now. Yeah, yeah, that's definitely coming up. In fact, with the first derivative test, which then goes right into graphing. We talk about sign charts in the first derivative test when we start talking about maximizing functions, and then we often talk about graphing them. We'll talk about optimization problems. The other question we like to ask is, how fast is the rock going when it hits the ground? And no, the answer is not 0. It's going 0 right after it hits the ground. But if it was going 0 when you hit the ground, then falling wouldn't be a problem. Right? But it is. So same sort of deal. We have to find out what time it is when it does the thing we're looking for, and then plug that time into the thing that we're trying to find. So when the rock hits the ground, what do we know? Exactly. Typically, these questions are answered by saying something is 0. The maximum is when the velocity is 0. The maximum height is when the velocity is 0. When the rock hits the ground, the height itself is 0. No, but that's not, well, let me clarify. Not the way I'm going to say it. But yes, depending on how you want to do it. But here's the thing. Our height equation is equal to this.
Okay, we already have
Right, exactly. So if you were to set up your coordinate system so that this was the ground, then your height equation would have been different. Your height would have been negative 16t squared plus 48t, which is not what we did. But if you did it that way, then you could say, okay, well, when it hits the ground, then I would set that equal to negative 64. That's how you could do it if you want to. But I definitely recommend making kind of, for lack of a word, the ground, you want to make the ground 0. Unless you're in 21B and you're underwater, and then you want to make like the bottom of the ocean 0. We'll talk about that later. But the bottommost thing you're dealing with is usually a good place for 0 to be. So we're gonna set, now I'll point out, we're gonna get the same equation either way, because whether I set my height equation equal to 0, or I set your height equation equal to -64, it's gonna be the same thing. Right. So then I'm gonna factor out the -16. I'm left with a positive t squared, a -3t, and a -4. And that totally factors as -16 times t minus 4 times t plus 1. So I either get time equal to 4 seconds or time equal to -1 second. Obviously, -1 second is not a sensible thing here. Although, I mean, technically, no, not technically. If you thought about being able to like travel back in time, right? If you go back down this way, 1 second before you threw it, you could have thrown it from the ground like that. That's kind of the way you could think about that if you wanted to. But we're doing this. We're going to plug that into the velocity equation because we want to know how fast it's going. If you plug that in, v of 4 is going to equal, sorry, where'd you go? -32 times 4 plus 48, which is -128 plus 48, which is -80 feet per second, which is the correct answer to the velocity when it hits the ground. It's going in the negative direction, so it has a negative velocity. Now, if someone said, how fast is it going when it hits the ground, or what's the speed when it hits the ground, we would say it's just 80 feet per second. When you talk about speed, you don't care about direction. Speed is the magnitude or the scalar component of this velocity vector, but the actual vector itself has a speed component and a direction associated with it. So be careful. So just be careful when someone says velocity, they really mean tell me the direction as well as how fast it is. Whereas if someone says speed, they only care about how fast it's going. Oh, I will just point out if you did plug in -1 second, you would get a positive 80 as your speed, which would have been how fast it was going if you threw it from the bottom there and kind of like so. So there's definitely some symmetry here. Right, if you'd actually thrown it from the ground here at a speed of 80 feet per second, it would go up all the way down and then come back down and hit with the exact same speed. Assuming, of course, there's not like resistance and all that, right? Like there's a lot of assumptions being made that we're not talking about